Are we adding and subtracting functions now? What would be a possible application for this? Anxiety plus depression equals personal misery index. Time spent on social media plus time spent daydreaming equals procrastination. Hope minus reality is illusion. Income minus cost is profit. Wait, what? This one actually makes sense. That's a legitimate application. I was trying to be sarcastic, and I accidentally stumbled upon a meaningful function. Income minus cost is profit. I guess it makes sense to do algebra with functions. Multiplying and dividing functions actually shows up a lot in real life. For example, if you're running a business, you might multiply the price per item by how many items you sell. That gives you your revenue function. One function tells you how much each thing costs, the other says how many things you sold. Multiply them, and you get the big picture. Or let's say you know the total cost of making X items. If you divide that cost by X, you get the average cost per item. That's a quotient of two functions. Very practical. So yeah, multiplying and dividing functions isn't just algebra. It's how businesses figure out if they're surviving or quietly going broke. The domain of a function is the set of all input values for which a function can produce a legit output. If you plug in something that breaks the math, like dividing by 0 or taking the square root of a negative number, you're out of bounds. When we perform operations like addition, subtraction, multiplication, or division with two functions, we have to respect both of their domains. The inputs have to work for both functions at the same time. And with division, there's one extra rule. We also have to make sure the denominator never becomes 0. A 0 in the denominator would break the laws of math, and possibly the universe. Forget this, and a zerophile will perform a celebratory dance in hell. In the first example, you are basically doing algebra with the outputs from two functions given the same input. You plug in 2 into both functions, get the outputs, and then combine those using the indicated operation. Nothing fancy, really. In the second example, all you have to do is putting g over f and finding the domain of the resulting rational function. Cannibalism is much commoner among mathematical objects than you might think. You can have brackets inside brackets, matrices that devour other matrices, and also functions that consume other functions whole for breakfast. Don't worry. I am just kidding. Functions work like machines with input and output, and just like machines, you can chain them. F of g of x means the raw material, x, is fed into the first machine, g. The function g does its thing, maybe stretches it, squares it, or adds glitter, and produces an intermediate output. That output is then fed into the second machine, f, which applies its own process. The final product is f of g of x, like a part that's been through two factory stages. The order matters. You wouldn't package the product before applying a coat of paint. In the first example, 3 is fed into g. G doubles it and spits out 6. 6 is then fed into f. F calmly adds 1. The final product? 7. Note that if we change the order, the result is different. Think of an egg as the input. Now imagine two processes, breaking and boiling. If you break the egg first, then boil it, you get a poached egg. The contents go straight into the water. A little messy, maybe, but still delicious. But if you boil the egg first and then break it, you get a hard-boiled egg. The result is different. Isn't it? That's function composition in real life. Same input, same steps, but the order changes the final output. A compositions domain is a two-part interview. First you must get past the gatekeeper, G, and then impress the CEO, F. One bad impression, and you're out of the domain. To find the domain of a composite function, here's what you do. First, write out the composition algebraically. Don't simplify it yet. Just plug one function into the other and see what it looks like. Then, ask yourself, what values of x are allowed in this expression? That's where all the important domain restrictions live, like square roots, denominators, or anything else that could break the function. In other words, check what can go wrong before cleaning it up. Simplification might hide the danger. The domain is based on the raw, unsimplified version. Working backward is like reverse engineering a product. You see the final result and ask, which functions were secretly behind this? In 1894, during a lecture titled Reflections on Nested Realities, a student asked Sir Isaac Factorton how radios actually worked. Factorton didn't blink. He sketched a diagram of nested functions across the blackboard. Waves converted to voltage, voltage filtered, signals decoded, sound amplified, etc., and concluded. Every outcome is the echo of layered processes. No truly useful function is simple, only well disguised. The whole auditorium was dead quiet. The student nodded, understanding nothing and very much regretting the question. Fortunately, the rest started applauding and broke the awkward silence.